Hi, welcome back to another lecture in process control automation. This is Nagarjuna. Today's topic is IO modules, input output modules. So let's look into the module types. So here, the modules are basically categorized into three. The first is the discrete IO module. The discrete IO module, again, it has further classified into two types: analog current module and the discrete current IO module, right? So what is a discrete module? Discrete module is basically, whenever you have information in a way of like 0 and 1, on and off, then this comes under the discrete. So most of the modules, most of the PLC modules will have, most of the PLC related operations will be on the discrete inputs and outputs. So here we have the analog current type modules and discrete current type module. Next, we have analog input output module. And again, in the analog input output module, we have two types of modules, that is a voltage module and the current module. So voltage module typically it range from 0 to 10 or minus 10 to 10. In current, industrial standard 4 to 20 milliamps or 0 to 20 milliamps. And then followed by special IO modules. So in today's lecture, we will look into all these three modules, IO modules. So first, we will see the discrete IO modules. So discrete IO modules. So here you can see in this picture, all these inputs, like say for example indicator, here in the bottom, this push buttons. The push buttons, the property is like just whether we can switch on or switch off, and similarly the selector switch or the limit switch or the proximity sensors. All these sensors, all these field devices will give you the output in the form of high or low. And similarly, when it comes to the discrete output, you can see this light indicators. The light indicators can be turned on or off, signaling column, and relays to turn on, turn off the loads, and the motor starter, start and stop, like that. So all these kinds of input and output will come under discrete. Now, when you look at the power or the voltage ratings of these modules, it comes with the different types, right? So this table I have taken from a reference textbook called Programmable Logic Controller by Frank Petruzzello. I'll indicate that reference in the end. So here you can see that the input, it has 12 volts AC and DC. 12 volts AC and DC, 24 volts AC and DC. So this AC is alternating current, DC is a direct current. So you will get these modules in both types. Similarly, 48 volts, 120, 230. So as per the user requirement, as per the user needs, so they can select any of this rating or any of this voltage type. So again, 5 volts TTL. TTL stands for transistor to transistor logic. Similarly, when it comes to the output, you can get again in a 12 or 48 volts AC module, 120 volts AC module, or 230 volts, 120, 230, like different ratings are available. Again, we can also see that 5 volts DC TTL logic, and 24 volts DC. Most widely we use this 24 volts DC output modules, right? Now, let's look into the discrete AC input module block diagram. So here is a diagram which represents how the AC input is going to be recognized by the module. So here you can see the source, the supply is 120, right? So here we have a 120 volts AC signal, and this signal, before it goes into the input module, it has to be converted into DC. So for that we are using this bridge rectifier. You all know that the bridge rectifier is used to convert AC to DC, right? And once we convert into the DC, then we use this Zener diode level detector, and then followed by optical isolation. I mentioned this optical isolation in my previous lecture as well, because there is no direct communication from input module to the CPU. We always maintain an isolation, and that isolation through the optical isolator. So we are going to transmit this data through this optical isolation. So now this binary data, this on and off type of data is going to be transmitted through this optical isolation. There is an optical isolation, nothing but here we use optocouplers. We use couplers here. So one will be the light source and another will be the light detector. So here at the source there will be a light emitter, and at the receiver there is a light detector. So when the light falls on, it is going to detect, right? And this logic circuit is going to identify that signal, and then it is further given to the processor for execution purpose. So here one LED light is displayed across the PLC to indicate that the status, whether it is on or off. So most of the circuits, almost all the discrete input output modules will have a LED indication. Now we'll look into another simplified diagram for a single input discrete AC input module. So here it's an example that normally, typically in any PLC there will be more than one inputs. So here is a one example, right? One simplified example for a single input. So here you can see that across the input there is a push button. The PB stands for push button. So, and you know the push button, when I press the button, the contact is on. So the moment when the push button is closed, the contact goes in, and through this bridge rectifier, as I mentioned, it is going to use for AC to DC. So the DC signal will go to the optical isolator and then followed by the digital logic circuit. In the same way, now each and every channel in the discrete AC, analog current discrete input, every channel is going to be treated in the same manner, right? So for example, if my module have a 4 AC discrete inputs, then all the 4 channels will have this internal circuit inside. So that's why it is a one of the simplified diagram for one channel, right? Now let's look into the discrete AC output module. So how the output module look like. So here the logic again, so this digital signal is coming from the PLC CPU. As I mentioned in the earlier also in the architecture, that based on the input, based on the logic, the CPU is going to generate one decision. So that decision will be in the form of 0 or 1. 0 means off, 1 means on. So this decision is given to the logic circuit, and the logic circuit will ensure the transmission of data again through optical isolation. This isolation is maintained in the input side as well as in the output side. The main purpose is to protect the CPU from these modules, because these modules are connected directly to the field devices. So we want the CPU safety. So this optical isolation, again, it is going to transmit the data, right? This is going to transmit the data through the light as a medium, and this electronic switch is going to recognize that data, and then subsequently we can able to get the information to the load. So we can able to connect, we can connect a relay, or we can connect a detailed logic, or whatever the mechanism required across the output. By using that, we can able to connect to a load, and we can make the load to turn on or turn off, right? So we can bring this voltage as per our requirement. So now again we will see a simplified diagram for a single output of a discrete AC module, right? So here again in connection to the previous diagram, so the digital logic from the CPU again through the optical isolation and through the track switch, okay, through the track switch, the signal will go to the output side, to across the output module. So here we can connect the load, and we can able to operate this load as per the requirement, right? Now next the next important module is analog module. After discussing about the discrete module, we will now discuss about the analog module. Before I move on to the analog module, once again I just want to give a quick summary of the discrete module. So any signal, if it is having a nature like 0 or 1, like on and off, or just like if you take any switch, we will make it as a high or low, then this type of operation we consider it as a discrete, right? So on or off, right? Next, when it comes to the analog input on output modules, the analog modules have a range, right? So it has a range, it has a voltage or current, and whether if you take the voltage 0 to 10 volts, unlike the discrete 0 and 1, the analog has a range 0 to 10. right? Similarly, if you take the current, then 4 to 20 milliamps or 0 to 20 milliamps. So it doesn't have like a 0 and 1, it has a range. So here one example of the analog input output module. So here you can see there is a level tank. So this level, I mean here the tank and the level is going to be measured by using one ultrasonic switch. So here is by looking at these waves, we can able to understand that there is an ultrasonic sensor which is going to emit these waves, and based on these waves and we can able to measure the level. So here this level transmitter is going to give you an output in the form of a range, but not in a 0 and 1, because our interest is not to check whether the level is there or not. Our interest is to check the level, how much level inside the tank. So this level transmitter will give us a range, right? So let us say the range is 0 to 10 volts, and physically if you consider that the level, say for example, if this total height, if it is say for example 100 centimeters, so it means that at zero it gives us 0 as a voltage, right? And when the tank is full at max, at say at 100 centimeters, it is going to give us 10 volts. And say for example, if the level is 50 centimeters, then the output will be 5 volts. So like that, the transmitter is going to produce the output. So now this output, this analog input signal is given to the CPU, I mean the PLC CPU. So here the processor will perform the execution on this analog input, and then based on that, most probably here we use the PIDs, proportional integral derivative, right? And after that, the decision has been generated, and that is given to the analog output module. And what the analog output module will do, taking the digital input from the processor, it converts back into the analog signal, right? So here analog input module, it takes the analog input and then it converts into discrete, it means digital, right? It converts into digital, because the PLC is a digital device, it understands only the digital data. So this analog signal is going to be converted to digital, so that is done by this analog input module. And PLC, once the processing is done, then again this digital data again converted into analog, and again converted into analog. So that is again done by analog output module. So in another way, we can say that analog input module will have a built-in A to D converter. Similarly, an analog output module, right, it has a built-in digital to analog converter. Simply to say, this AI and analog input and output module will have a built-in data acquisition systems, right? And another point I would like to mention here, say for example, if your module have four analog input channels, if it is having a 4 analog input channels, then each and every channel, right, will be treated separately. So each and every channel will be treated separately, and each and every channel has its own dedicated ADC. Each and every channel will have its own dedicated ADC. Same is the case with the analog output. So in the analog output also, it has a digital to analog converter. So if you have 4 channels, then 4 DACs we can expect, right? And it's very clear that when you compare the cost of the discrete module versus the analog module, the discrete modules will cost less when compared to analog module. Why? The reason is simple. Discrete module, the mechanism, the circuit is very simple when compared to analog. In analog, we have this data acquisition. That's the reason why the cost is on higher side. And when it comes to the application, discrete modules mostly used for the switching applications, and analog modules are used for the process control related operations, right? Now let's look into the signal type here. So here in the signal type, we can see the span or the of a signal, analog signal. So we can have a say if it is a bipolar, so we can have a from minus 5 to plus 5 or minus 10 to plus 10. Bipolar is nothing but the range starts from the negative. If it is a unipolar, the range starts from the 0 onwards, right? So minus 10 to plus 10, minus 5 to plus 5 in bipolar, and 0 to plus 10, 0 to plus 5 in unipolar, right? And you can also see the resolution. What is this resolution? The resolution is the minimum voltage where a module has to respond. See, for example, if I'm using a 0 to 5 volts analog input module, then the minimum, if the voltage, if it is below 0.3, then the module is not going to respond. So the module will respond only to the minimum value of 0.3 because the resolution is mentioned. So clear. So that's what the resolution is, right? Because it's all about, we are converting analog to digital. Same is the case, digital to analog. So resolution, those who have an idea about the DACs or ADC DAC, they know about what is the resolution is, right? So now next thing is we'll discuss on this sensor and analog module and supplies. Sometimes we have a special modules where for the when we interface a sensor to the input module, right? So the sensor, sometimes it is classified into two types, passive and active. If it is active, we don't need to give any excitation. If it is a passive, we need to give some excitation to the sensors. This is very quite common, right? But unfortunately, most of the sensors are passive. Very few are active. So what to do with these passive sensors? For these passive sensors, we have to provide a supply, right? We have to provide a supply to the sensor. So there are some modules in the market where the module itself will give you the power supply or whatever the power required for the sensor. The module itself will decide. It is going to generate. There are some modules where we have to connect supply to the sensor directly. So here you can see the first one, sensor supplied power. Sensor supplied power, which means to the sensor we are giving supply directly. Which means the module is not going to provide that supply, right? So module is just expecting some signal from the sensor. So that signal from the sensor is obtained only provided if you connect any power supply to the sensor. So you can see here clearly that the power supply is connected to the sensor. Now the sensor is powered up and sensor is able to sense the physical parameter, and as a result it is going to generate some output, and that output is taken by your module, your analog input module. Very simple. Next, we have other image, that is module supplied power, which means now you can see the sensor is not given any external, it has not given any supply or directly, but instead what happening is from the module, inside the module there is a power supply, there is a built-in power supply. So here this supply will go through this channel, through this terminal. So it means now the sensor is seeking the power from the module, which means, so here there are two types I mentioned, right? So this module is not going to provide any supply, just whatever the sensor is giving it is going to collect, whereas this module is responsible in providing supply to the sensor. At the same time it receives the sensor data as well, right? So most of the current loops will work in this way, right? And obviously these modules will cost more when compared to this module. Clear? Now, next we'll see another example, analog input module circuit, right? Now here there is one temperature probe, right? So you know that the temperature probe is going to measure the temperature signal, right? Now this sensor is when it is exposed to the physical parameter, as a result, some physical property changes will occur. There is a basic sensor property, and then it is going to transmit a signal. So that signal can be voltage or current. So in here it is a voltage, so 0 to 10 volts, right? So this 0 to 10 volts, it is scaled, right, in with respect to time. As we can say that as with respect to time, when the temperature increases, the value increases, right? The values will goes on, right? So this is a simple relation, right? Now we can connect this transmitter output directly to the terminals of the PLC, analog input module terminals, right? Then here is again another example, right? Here you can see that we are going to measure the level, so we use a level transmitter. So level transmitter is going to provide some analog input, the analog value, and that analog value will go as an input to the PLC as a input, or in a process we can call it as a process variable. Okay, process variable, or in short we can say it's a PV, right? So the output of the level sensor is a PV, and PLC will process on this PV, right? And we will give some set point, right? We wanted to maintain some level, so that is called set point. So at what level you want to maintain, that is nothing but a set point. So now here the controller simply it calculates the error. So error, it is nothing but SP minus PV, right? So set point minus PV, right? So based on the error, the controller will take the action. If it is a positive error, positive action will be taken. If it is a negative error, negative action will be taken, right? So once the action is taken, the output is called control output. It is called control output. Okay, so this output is given to the final control element. So here the final control element is the wall. Okay, final control element is the wall, a control wall. So basically we use one a converter I to P, because this wall, basically walls, it operates with a pneumatic signal. So the controller is not it doesn't provide a pneumatic signal. So the controller output, the current, let us say the current will go to the I2P. So what happens here, the current is going to be converted into pressure. So that pressure goes to the wall, and here the wall opening closing takes place, right? So this is how this operation will goes on continuously, and in fact I can say this is one closed loop operation with single input and single output. It's a closed loop operation where continuously I can able to monitor the level, and continuously I can able to track my set point. Clear? So most of the continuous process we make use of the analog inputs and output, and for most of the switching applications we make use of discrete input and discrete output modules, right? So here you can same thing you can see in the another example, that the temperature probe, which measures the temperature signal, and here is given to the analog input model. And here, yeah, scaling is one of the most important things. So scaling, what is scaling? Scaling is nothing but, you can see that so if this probe is giving an output in the range of -10 to 10, so it's a bipolar, right? We discussed just now what is the unipolar and bipolar. So the sensor is giving you a bipolar output, so -10 to +10, because the temperature sometimes it may go to the negative as well, from -100 to +200. So the sensor output will be a bipolar range. So when it is -10, we can able to get a value, a digital value of -32K, right? If it is a +10, we get a digital value of +32K. You might be surprised, like when I'm giving this -10 and +10 across the input module, then why I'm getting this digital value in the PLC? This is very simple. As I told you that analog input module has a built-in ADC. It has a built-in ADC, analog to digital converter. So when this analog input is given to this ADC, the ADC will convert that into digital, right? And this digital value depends on the resolution. Sorry, the digital value depends on the bit, right? How many bit ADC it has, right? So in the market we'll get 8-bit, 12-bit, 16-bit, like that. So depending on the bit size, the digital value is going to change, right? So this is how it works, right? So next we will look into the special IO modules. There are so many types of IO modules available in the market based upon the needs, based upon the requirements. So all these modules are being developed. Now first we'll look into the high speed counters. The high speed counter, why it's a high speed counter? You can see here it is going to count 1 lakh pulses per second, so it's very fast. Normal counters cannot do such a, they cannot run at that speed. So here we in some applications demand for counting will be more. That's why we use this high speed counter module. Next, we have a thumb wheel module. Thumb wheel module allows the use of thumb wheel switches. So here is a image, right? Normally it is used in the conveyor belt. So whenever the product moves on, we can get the count. At the same time, this count is also being projected across the PLC. Next, we have a TTL module, transistor to transistor logic. So whenever the signal communication takes place in the transistor TTL level, then again this module helps a lot. Then for the digital application, we have the encoder counter module and the ASCII module. ASCII stands for American Standard Code for Information Interchange. So these modules mostly, we can use it for the barcode readers and printers and display purpose, right? And then moving on, we have a stepper module. If you have a stepper motor in your application and if you want to run this motor, and then we need the stepper motor module. Then again, BCD output module, binary coded decimal output module, enables the PLC to operate device that requires BCD signals, like for example 7-segment displays. Then PID module, proportional integral derivative module. Most of the continuous process will be controlled by using this PID. So if you have this dedicated modules in the PLC architecture, then it helps a lot. Then we have a motion and position control module, and this is used in the robotic applications. And next, finally, for the communication purpose, we have the communication module. So like that, you can see for every need, for every requirement, we have a special modules, right? That's it for, the IO modules. All the pictures, images I have taken from these 2 textbooks. So here is the references. Thank you for listening. We'll continue in the next lecture.
Like, share, comment, and subscribe VNR Digital Learning Resource YouTube channel.